Okay, so here is the last video, video 5 of class 6, dealing with the introduction to fluid kinematics. And we're in section 4.4, and we're not going to do a lot with this, but this is just for information, stuff that you might want to know about and might become relevant as we move forward. So we want to start talking about the different motions that can be possible within a fluid, right? So we already talked about velocity and acceleration here, but let's talk about the deformation, the types of motion and deformation in fluid elements. And little pictures are good to sort of translate pictures. So we talked about translation. Basically, we've been talking about translation, but there's also rotation of little, we could take just a little chunk. It doesn't have to be an individual particle, but you could think of it as a grouping of particles, if you'd like, of fluids moving. So we have rotation as a possibility. We can also have linear strain, and we can have shear strain. And it's, very similar to things that we dealt with in solid mechanics. And just to extend this stuff, I've taken a class called Continuum Mechanics, where I just try to just say if you take a big look at something, not too far off, but so we're zooming into some of a piece and seeing how something that's considered a continuum might behave. The solid mechanics and fluid mechanics have a lot in common in terms of the treatment that you could do to try to quantify the motions. So instead of being rigid body motions, we can also have deformable motions, and that could happen in fluids, or it could happen in solid mechanics, and something in between too. So anyway, so we could have like a general type of motion. So if we have like this little square right here, we could see the new position that it could possibly come into. So we want to try to use vector calculus to try to break this down a little bit. So and here's like an example, right? So here's like streamlines that we're getting used to seeing. You can see there's like a stagnation point here in the center. But if we had like maybe a fluid as it moving from one position to another position, it could actually change shape to some extent, right? So that's a graphical thing. And I'll bring up vorticity and rotationality. I don't know if I'll talk about rotationality, but let me switch over to my document camera, because I put out some equations. So here's the figures that we've already seen. These are the Sengel. So let's just start with our vector right here. So here's our field equation right here, where this isn't just one particular particle. This is a field of particles. If we want to figure out the rotation of something, we can find it by taking these like half motions right here, where I don't really have this broken down into the derivation of this, so it's really just laying it out there for you. But these are sort of like the strain rates, right? With how the W, so in the X direction here, you could see that the change in W with respect to Y minus the change in V with respect to Z. So you can see there's no U terms or X terms right here. We're kind of looking down at the piece that's moving. So this is a rate of rotation vector in Cartesian coordinates for all three directions. And we'll see that soon, as that's going to be very related to our vorticity vector. This is just the second cousin of them. And so I'm playing these in order as they show up in the book. So that was the rotational one right up here, some rotation going on. And then here's a strain rate, a linear strain rate, right? So here's the linear strain, and here's an equation that we might want to just look at, right? So this is just like strain that you'd have in mechanics of materials, except that it's a rate, right? So it's really sort of the deformation over the original position, right? Or how the deformation, but this is a deformation per time, right? That's what you could think of this velocity component. So it's the strain, but it's a strain per time. So it's a strain rate. Same thing in the y direction, and same thing in the z direction. And notably, they don't really have any Poisson's ratio kind of relationship as they're showing. They seem to be independent from each other. Okay, so that's one that you might want to describe as a linear strain right there, right? So, but of course a strain rate. And then lastly, we could do the shear strain rate in Cartesian coordinates. So like you see, here's a epsilon xx and epsilon yy, epsilon zz, where here is these, and these are really sort of like the slopes that are taking place. So like when we think about strain, when it comes to shear strain, it's really the angles about which this thing occurs, right? So it's really for an angular type of thing. And similar, like as we noted up here, we would say we would have the velocity in the x direction component as a function of y, right? So there's going to be sort of a slope going on right there, and that's what happens here. It's sort of an angle or a slope that's taking place. And then the same thing is true with the velocity in the y direction and with as its rate in the x direction. So this is also a slope that we want to go, right? So because, you know, you can think of it as, you know, there's a, here is the u and here is the v as it's going right here. So you want to try to find how this u is changing as a slope in the y direction, and you want to change that, see how this v is changing as a slope in the x direction. So we're looking at a particular plane going right here, and the same thing happened in the zx direction, right? So we're looking at a particular plane for these, so we can see how the w is a slope in the x direction, and how the u is a slope in the z direction, and then lastly in the yz plane for this little cube that's floating around. So we want to get a little more mathy about this, and we have this thing called vorticity. So the vorticity vector, and I always forget which one this is. Sometimes I ignorantly call it squiggle. I like calling it squiggle. I think it's a psi. I think it is. I should look it up, check it up again. Which Greek letter that is. But it's our good friend, this operator right here, which would the gradient look like? The gradient was this, is sort of it's the same operator, but now we're crossing it instead of dotting it against the velocity vector. And what that ends up doing is giving us, they call it the curl, and you could even think of it, I always think of it as a curl like that. It's curling onto the thing, and it's just the cross product of that same operator. Or that operator, if you'll recall, was the, let's see, I'm going to do this the right way. It's the partial derivative of whatever to x plus the partial derivative of whatever to y plus the partial derivative of whatever to z. But now you're going to set it up and curl it. You apply this thing in against the velocity vector, and when you do that, you know, we're going to set up like probably a matrix where you go I, J, and K, and then you set up this guy right here on this column, and then you set up the velocity, the U, V, and W across there, and you take the determinant, and of course the right-hand rule is going to give you sort of what the spin is going to be. And it turns out that rate of rotation thing right there, the one that we just kind of mentioned back over here, we'll see that it's this rate of rotation is actually 1/2 of the curl, right? So vorticity is a measure of the rotation of a fluid particle, and it's equal to twice the angular velocity. So if you want to think of the definition of vorticity, is right in there. One of the reasons why this comes up is in some of the more higher level or advanced things that we'll talk about. And once again, this is just an introduction to kinematics, so it's sort of important that we kind of like throw this stuff underneath our nose and get a little bit familiar with it, and maybe we'll forget it, but then we're going to introduce it again, and you'll become more familiar with it and be able to use it for something, or at least be able to comprehend it better, having already seen it once. the reason why we bring it up is a lot of times we need to make assumptions in order to apply certain fundamental equations when we want to try to solve something. And that's one of the many things that will help to make, a simplifying assumption is limiting ourselves to what's called irrotational flow, right? Because so when the vorticity vector is equal to 0, we call that flow irrotational, and we're able to use it, that simplification, to be able to solve problems more easily. Like if we kept that, if we were applying it to something that was rotational, the math would get too hard to actually solve the problem. So we can limit ourselves to areas where the rotational is either there's no rotation, or the rotation is insignificant enough that we can make a model and solve it, like, just because it's just too difficult to solve with it. So here's one where we have a flow field, and here's the wall, and we know that we have a no slip condition when a fluid's passing along a surface right here. There's no slip right here. So there's a velocity profile, and we have something called the boundary layer that will form, right? So this is a snapshot for this location, but you'll see that there could be another one over here where right in there. But when we get far enough away from this boundary condition, we can see that we sort of have this even flow. And a lot of times inside this boundary condition, we might have turbulence and other things, and we'd have the rotation of things. And so we would like to, we might be able to solve stuff directly inside the boundary layer, but we might be able to solve stuff outside the boundary layer. One idea of, like, if that doesn't mean that things aren't rotating. It's just that, so the things can spin, but they have no local rotation. So here's this classic type of description, or you could see where we have here is rotational flow, but here's an irrotational flow that is rotating around. So it said it's irrotational, but it is rotating around. Now, this is an impossibility, right? This cannot happen in terms of, like, especially right here. The assumption of this makes there an infinite velocity here in the center, which is just not possible. But once again, you have to kind of think about, like, some of the applications of some of these equations would often be for, not true everywhere. We're just going to look maybe at a location of something. And so we're able to look at a particle that is moving in an arc, and so we able to solve it under the assumptions of irrotational, even though it is making an arc, right? We can't do it over here in reality, but we can make the assumption that, okay, even though it is moving, it's staying in one spot. And now the classic example that they like to use in books quite often is like a Ferris wheel, right? So in a Ferris wheel, all the seats stay upright as it's rotating around, as opposed to looking down onto, say, a merry-go-round, where everybody will be, in effect, rotating what their orientation is going to be as they move around. So here is what the vorticity vector looks like in Cartesian coordinates. A lot of times it's easier for us to look in 2 dimensions right here. So this is the one, and of course, in 2 dimensions, it's rotating about the axis that's coming out of the page. So just a little bit of a discussion, sort of introduction. I encourage you to read through the author's better description than mine of some of these things. Do I have any more slides that are applicable here? No. Basically, this is saying the same thing. Likewise, in the vorticity region, the flow is 0, negligibly small is okay. So anyway, I think that's all we have. Vorticity, it's an important thing, and we will discuss it and describe it some more later in the semester. And thus ends class number 6. Thank you very much.